Hello, chemists. Today we're going to be talking about the ionic product of water, Kw, um, almost our last K value. So I told you there'd be a lot of K values. Kw is another K value, and it is a description of what's going on in water with regards to two things, with regards to hydroxide and hydronium. So in pure water, water that doesn't have anything else in it, there's a little bit of hydroxide and there's a little bit of hydronium, but really, really small amounts, and those are in equilibrium with the liquid water. This is something we've discussed before. At 25 degrees Celsius, we can measure how much hydronium and how much hydroxide is present. Of each of those, there is 1 times 10 to the negative 7th moles per liter present in pure water. So 1 times 10 to the negative 7th moles per liter hydroxide, 1 times 10 to the negative 7th moles per liter hydronium, same amount of each. However, that's not quite what Kw is. Kw is the product of the concentration of hydroxide and the concentration of hydronium. So if we take those known concentrations, 1 times 10 to the negative 7th for both, and plug those into our usual K value calculation, both of the products divided by the reactants, in this case water, which we don't include, we get this equation here. Kw is equal to the concentration of hydronium times the concentration of hydroxide, and that is equal to 1 times 10 to the negative 14th, because 1 times 10 to the negative 7th here, 1 times 10 to the negative 7th here, equals 1 times 10 to the negative 14th. That's at 25 degrees C. If we change the temperature, the Kw will change. But if it doesn't tell you, assume that it's at 25 degrees. And we can use it to calculate the concentration of hydronium if we know the hydroxide and vice versa, because now we know the relationship between H3O and OH minus for a given pH. So if we calculate the hydronium concentration in a solution with a hydroxide concentration of 5 times 10 to the negative 5th moles per liter, then we can use that to get the concentration of hydroxide. So we know hydrocide. It is 5 times 10 to the negative 5th moles per liter. And we just plug that into this equation up here for our known Kw, which is 1 times 10 to the negative 14th, rearrange, and we can get that the concentration of hydroxide, or hydronium, is 2 times 10 to the negative 10th. Another example, once we know the concentration of hydronium, we can find the pH from that using the equation we practiced before. If we increase the concentration of hydrogen ions of hydronium, then the concentration of hydroxide must decrease because those are in equilibrium. You can kind of picture that like this. At equilibrium, you've got equal quantities of both, you're here. If you increase the hydroxide, you must decrease the hydronium. If you increase the hydronium, you must decrease the hydroxide in order to remain at equilibrium. And if you increase the hydronium, you will increase the acidity. If you increase the hydroxide, you will decrease the acidity, increase the basicness. The pH will be less than 7 for an acidic solution or greater than 7 for a basic solution. You know all of that. For an example, you've got the sodium hydroxide. It's a strong base, which means it fully dissociates into sodium and hydroxide. And for a 1 mole per liter solution, we know that the concentration of sodium and the concentration of hydroxide are equal to each other, and both of those are 1 mole per liter, because 1 mole of sodium hydroxide will dissociate completely because it's strong into 1 mole of sodium and 1 mole of hydroxide. So we take our Kw equation that we just learned, and it's the concentration of hydronium times concentration of hydroxide. We know the concentration of hydroxide from up here. We know the Kw because it's 1 times 10 to the negative 14th. And we can just rearrange, which is what we do here. And we get that the concentration of hydronium is 1 times 10 to the negative 14th. We can use that to find out the pH. In this case, by doing the negative log of the concentration, we get the pH is 14, which is quite basic, which is what we'd expect from sodium hydroxide being a strong base. The end.